Hello again, and I hope that you are enthusiastic and full of energy to continue, full of beans to continue learning the basics of statistical mechanics applied to chemistry. Well, and I have prepared a few problems for your consideration, and I also hope that you find them interesting. So let's get down to the nitty-gritty, as they say. Well, here's the first problem. We've got a molecule which can be found at two different energetic levels, with energies being equal to 0 and 300 inverse centimeters inversely. Inverse centimeters respectively. And they ask us to calculate the probability of the molecule being found at the higher level at temperature which is equal to 250 degrees Celsius. Okay, before we get down to the solution to this problem, I would like to say a couple of words. Whenever we deal with the distribution of molecules, in most cases, chemists have to deal with or handle Boltzmann distribution, okay? And you also remember that in the formula of Boltzmann distribution, exponents involved into this formula are raised to degrees which have energies, right? Energies of corresponding levels. And the measurement units of these units are not centimeters raised to -1 absolute, no, not inverse centimeters. They are joules per molecule, not per mole, by the way, but per molecule. For that reason, in practical terms, we need to get the levels of energy, the values of the energy given in joules per molecule from inverse centimeters. And this is our first step. Let's do that right now. You need to get the factor which gets joules per mole from inverse centimeters. Here it is. 1 inverse centimeter is equivalent to 11.931 joules per mole. Okay, and it's I hope that it's obvious to you that 0 centimeters inverse centimeters corresponds to no joule per mole, right? 0. But if we've got 300 centimeters inverse centimeters, in this case, we should multiply this value by this one, and we will get some value of this energy, but not in inverse centimeters, but in joules per mole. So I have already done it, and it's equal to 3,579.3 joules per mole. But again, we don't need joules per mole, we need joules per molecule. And in order to get this number, we have to divide this value by the Avogadro constant, which is equal to 6.022 times 10 raised to 23rd to the 23rd, right? So let's do that. In other words, we can write immediately that epsilon sub 1, which corresponds to the energy of the ground state, is equal to null or 0 joules per molecule, and epsilon sub 2, which corresponds to the high energetic level, is equal to 3,579.3 joules per mole divided by 6.022 times 10 raised to 23rd to the 23rd moles raised to -1. Okay, in this case they cancel each other, and we got joules. And your calculators should show you the same numbers I got is equal to 5.944 times 10 raised to the -21st joules per molecule, or just joules. Okay, so we got these two values of the same energetic levels, and this time measurement units, the measurement units are joules, but not inverse centimeters. This is what we need to do. Now, our second intermediate calculation step is to calculate so-called Boltzmann factors, just to make our calculations a bit easier to deal with. So, exponent raised to minus epsilon sub 1 divided by k times t, right, is equal to exponent minus 0 k2, because we have just found that 0 corresponds to 0 joules, but it means only one thing: is e raised to 0, it is equal to 1. This is the Boltzmann factor for the ground state. Now, we are going to calculate the Boltzmann factor for the higher energetic level. So, exponent raised to minus epsilon sub 2 divided by k2. Okay. Just want to say, remind you that k is Boltzmann constant, right? Okay. It's exponent minus 5.944 times 10 to minus 21st divided by 1 to minus 23rd. And the temperature is, remember to get kelvins from Celsius by adding 273, and that will give you 523. Okay, and your calculators should show you, if I'm not mistaken, 0.439. Okay, now the Boltzmann distribution formula itself, n. So they want us to calculate at the high level. That means n1 over n is equal to exponent raised to minus e sub 1 divided by k 2 over the same plus the Boltzmann factor for the higher level. It is 0, right? I'm sorry. This is for the ground state, and this is for the higher level. Okay. Now, we have just calculated this Boltzmann factor, which is equal to 0.439. This factor is equal to 1. Here it is, plus this one. Okay. And here, if you've got your calculators, it will show you that it's equal to 0.305. This is the answer. In other words, the probability of finding a molecule at a higher level equals 30.5 or 30.5%. This is the answer. Let's proceed to the next problem. So we've got the molecule which can occupy two energetic levels with energy supplies equal to 0 and 600 inverse centimeters respectively. They want us to calculate the temperature at which the number of molecules occupying the higher level is half that at the ground state. So let's start from some designation. So n sub 1 is the number of molecules which occupy the ground state, okay? While n sub 2 is the number of molecules which occupy the higher energetic level. Now, from the problem we understand, and I hope that you understand too, that n sub 2 over n, where n is the total number of the molecules in the whole system, is the, let's say, concentration, yeah, just to make the things easier for understanding. This is the concentration of molecules at the higher energy level, while n sub 1 over n is the occupation degree of molecules of the ground state, right? Now, we know that the number of molecules occupying the higher level is half the number of molecules which occupy the ground state. For that reason, we can write that n2 over n is related to n1 over n as a half, okay? Or we can write from this relation, we can write that n sub 2 divided by n sub 1 is equal a half. I hope that it is as clear as the day. Now, we also remember, let's apply the Boltzmann distribution for this and for this. We can write that n or sub 1 over n is equal exponent raised to minus epsilon sub 1 or divided by kt divided by the sum of this okay, and then of this exponents. The same can be written for n sub 2 over n, but the denominator is equal to exponent raised to minus epsilon sub 2 divided by q2. Okay, now let's apply this and this to this. We will see that exponent raised to minus epsilon sub 2 over q2 okay. Mhm. I hope that you understand what I'm writing. And this is equal to half. Yeah, when we divide something by a fraction, so the fraction finally gets upside down, and we will see that this and this will cancel each other, and finally we'll get that e, or exponent raised to epsilon 1 over kt, okay, times e raised to minus epsilon sub 2 divided by kt is equal to raised to the minus first degree. Okay, the bases are the same. For that reason, we just sum these two. We'll get that exponent raised to epsilon 1 over kt minus epsilon sub 2 over kt is equal to 2 raised to minus first. Okay. In other words, it's equal to, or it corresponds to this. But we need to get we need to get the temperature, right? To do that, we take natural logarithm of the two parts of this equation. Okay, and these two destroy each other, and we get that A1 minus E sub 2 divided by A2 is equal to minus natural logarithm of 2. But the energy of the ground state is equal to 0, right? And it means that minus epsilon sub 2 is equal to minus natural logarithm of 2 times k times 2. Minus by minus gives us plus. And from this equation, we can get t. T is equal epsilon sub 2 divided by k and by natural logarithm of 2, right? And again, we can see that to continue our further calculations, we need to transform inverse centimeters to joules per molecule. And we have done it already. Let's do that now. Again, 6. We multiply 600 to 11. 0.931. Okay, and divide by the Avogadro constant, which is equal to 6022 times 10 raised to 23rd to the 23rd, okay? And we divide by the Boltzmann constant. It's equal to 1.34 times 10 raised to minus the 23rd and natural logarithm of 2. If you take a calculator, you will see that it's equal to 1,242 Kelvin. And this is the answer. At this temperature, the number of molecules occupying the higher level is equal to half of that number, which is corresponding to the number of molecules occupying the ground state. Thank you. So I hope that you still have enthusiasm to continue. And here is another problem. Hold on a second, please. Hold on a second. Here it is. The problem is the following. So we've got a system. The system can have only discrete energetic levels, each having energy equal to n times E, where n is an integer, which can be equal to 0, 1, 2, 3, etc. They want us to calculate the probability that the system has energy supply n times E, and also they want us to compute the average energy of the system in 3 cases. When the temperature is low, in this case, they believe that K times T is equal to 1/10 of the energy. At medium temperatures, when K times T is equal to E, and at high temperatures, when K times T is equal to 10 times E. Again, I want to emphasize that K stands for Boltzmann constant, okay? Now, it's a very interesting problem. Well, it's partially covers the previously given problem, and at times I will refer to what we have done previously, okay? Now, let's start from the first one. It's low temperatures. Low temperatures. Why am I not saying anything about the first question where they ask us to calculate the energy level of the probability that the system has energy supply N times E. I will explain to you why. The thing is that the probability that the system has energy supplies N times E is equivalent to calculation of energy level population calculation. Energy level population. And this is what we're going to do right now. In other words, before we calculate the average temperature of the system at low temperatures, we will have to calculate the energy level population, and that automatically answers the first question. Okay, now let's start from the beginning, and we remember that before we apply a Boltzmann distribution equation, we have to calculate the values of Boltzmann factors for each of the energy levels. Okay, now we've got level 0, level 1, level 2, etc. These are their numbers. The first one is the ground state, which has a number 0. For the ground state, n is equal to 0. For the next one, somewhere deep in mind, actually, frankly speaking, I should admit that I consider it as the second, but formally in thermodynamics, in statistical thermodynamics, we consider that the ground state has the number of 0, and the next one is 1 only, not 2. Okay, now let's start from calculation of Boltzmann factors, and for the ground state, traditionally it's equal to 1 because the energy level is equal to n times E over kT. But for the ground state, n sub 0 is equal to 0. That means that we've got E raised to 0, and exponent raised to 0 is equal to 1. Okay, any number except 0 raised to the degree of 0 is equal to 1. This is what you must know from mathematics. Okay, we have finished calculations of the ground state Boltzmann factor, which is equal to 1. Now let's proceed similar things for the other discrete energetic levels. E, which stands for exponent, raised to minus epsilon sub 1 over K2 is equal to E minus, instead of epsilon sub 1, I write n sub 1 E over K times T, right? But N1 is equal to 1, and that means minus E times KT. But we are dealing with low temperature, with the low temperature intervals where K times T is equal to a tenth of E. And now instead of KT, I substitute 0.1 times E. And I've got finally exponent raised to minus 0.1, a tenth, raised to minus a tenth. Okay, I've got it. I hope that is clear for you how I got it. Now we similarly or likewise, we do the same things. In other words, we continue calculating Boltzmann factors for the other factors. I'm sorry, for the other levels. So exponent raised to minus epsilon sub 2 times Kt is equal to exponent. Instead of epsilon sub 2, I write n sub 2 times E. And instead of Kt, I'm writing 0.1 times E, because again, we are dealing with low temperature interval, and instead of N2, I write 2, and that means E minus 2 times E over 0.1 E. these e in the numerator and this e in denominator cancel each other. And finally, I've got e raised to minus 20. Oh my God, I made a mistake here. I'm sorry. Of course, e raised to minus 10th. And here I've got e raised to minus 20th. Okay. Now, similarly, I hope that no need to write down the full complete calculations. I can write that for the next um, energetic level. I can write that it's equal to e raised to minus 30, right? And then I will get e raised to minus 40th. Okay, these are the bottom factors. Okay, now now we are ready. Now we are ready to calculate the energy level population. So let's start from the ground state. We can write that n sub 0 over n. Again, when I say that n sub 0 stands for the number of molecules which occupy the ground state, whereas n, capital N, stands for the total number of the particles which occupy all the energetic levels. Okay, and now we are writing the Boltzmann distribution formula. It's E, and if we're dealing with the ground state, it's E raised to minus epsilon sub 0 over k times t. And here we write epsilon E raised to minus epsilon I over kt. You may ask me why I'm not writing down a G, which stands for statistical weight. It's because nothing is said about it, and automatically I consider that Gi is equal to 1. In other words, non-generate levels are given in this problem. However, if something is said about degeneration, so we also should take it into consideration, but not in this assignment, not in this problem. Okay. Now, what we do is to substitute with what we've got. This Boltzmann constant is equal to 1, okay? And here in the denominator, we write down all the exponents which we got. It's 1 plus e raised to minus 10th plus exponent raised to minus 20th plus exponent raised to minus 30th and plus exponent raised to minus 40th. You should understand that these numbers are very, very small, and roughly you can say that this fraction is very close to 1. Not exactly, it should be slightly less than 1, but anyway, very, very close. And if you have a good calculator, it should show you that the first, or the ground level population, is equal to 0.9999546, which is very close to 1, actually. And it is clear because these terms are very, very small. And in practical calculations, we could consider them equal to 0. Okay, okay. But this is only the ground state level population. Now let's proceed to calculations of the other energy levels population. So the next one is N1 over N. In this case, we write the Boltzmann factor, which is related to the next level. Okay, and here we write this sum. Again, I just want to remind you that this symbol is taken from the Greek alphabet. It is sigma, and in mathematics and physics and chemistry, it means sum minus epsilon I over k times t. Okay, and we've got, for this, we have calculated here, it's exponent raised to minus 10th And here we've got the denominator, the same, blah, 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 blah. Okay. I'm sorry, I just don't want to write down this in detail, but you'll have to, okay? Not to lose marks, you'll have to write this to the end, this one. Copy down and plug it here. Okay, and with a calculator, we got it. It's 4.5002 times 10 raised to minus 5th. You see? And for the others, n times, I'm sorry, n sub 2 over n, we do similar calculations, but for the next level, energetic level, we remember that it's very, uh, it's actually from, uh, oh my God, it's from uh, physics, which is related to particles, right? And whenever we deal with particles, we have to deal with discrete amounts of values of something. Okay. E raised to minus E epsilon over 30. So this time it is E raised to minus 20. Yes, it should be minus 20. Yeah, here it is. 20 over this 1 plus blah, 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 blah. Okay. And that will give us, what is it? 2.061 times 10 minus 9. And if you do similar calculations, we will get that m sub 3 over n is equal to 9.357 times 10 raised to minus 14th, and n sub 4 over n is equal to roughly 4.25 times 10 raised to minus 18. As you see, the population of these of high energetic levels is getting lower and lower, considerably lower. Yeah, and this is the answer to the question about the probability that the system has energy supply n times E. We have just done it because it's equivalent to calculation of energy level population. Okay, and now we're proceeding to the next question, which is to calculate the average energy of the system at low temperatures. Let's do that. So the formula is like this: the average. The symbol of average in physics is this one. The average of the temperature, and it's equal to sigma of products epsilon I, which stands for the energy of each of the energetic levels, times energy level population n I over n. And now we are ready to start calculating the average average energy. So the energy of the ground state is equal to 0, but let's be forward to the end, and we will have to write it down anyway. It's 0 times, and the uh, energy level population of the ground state is equal to, here it is, 0.999, so sub 4, which means 4 nines, okay, 54.6, okay, plus. Now, the energy of the next ground state, oh, sorry, of the next level is exponent raised to minus 10. And now we should multiply it by 4.54. Uh, I'm sorry, I'm doing something wrong. No, 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 no. Of course, no, 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 no. I'm just writing the energy of that level is equal to ME, M times M sub 1E, right? And now I'm writing the and it's equal to 1, yes? And its Boltzmann factor is equal to, not Boltzmann factor, its population, right? Is equal to 4.5002 times 10 raised to minus 5. Yeah. Okay. Yeah. Now we do the same with the next level. It's n times n sub 2 times a times times this one, I guess. Yeah. It's 2.061 times 10 raised to minus 9, and n2 is equal to 2, right? And similarly, we can write, instead of m sub 3, I can write 3 times energy, yeah, uh, because this is the amount of energy, n times E. Instead of n, I put down 3 times E, and now the population, level population is equal to 9.357 times 10 raised to minus 14, etc. But you should understand that this term, not to mention the last two terms are very, very small, and in practical terms, they play no role in calculations. In other words, we can neglect these terms, the last three terms, and this one is equal to 0 because n sub 0 times E is equal 0 times E. Yes, it should be written like this. And this whole term is equal to 0 therefore. And we can write that the average level of energy of the whole system at low temperatures is roughly equal to 4.5402 times 10 raised to minus 5 times E. This is the answer. And we have just finished calculating the average temperature for the case when the temperatures are low. Now we should proceed to the second part of the calculations when the temperatures are medium. In other words, when the uh, product of the Boltzmann constant and temperature is equal to E energy. So let's do that. Let's do that. Okay. Now we continue to calculate for the second case when the temperatures are average or intermediate. Yes, a medium, intermediate temperatures. Now let's do that. The calculations are likewise. So in other words, the Boltzmann constant, the Boltzmann factor for the ground state is still the same. It's equal to 1. Okay. Now, the exponent for the next energetic level is equal to, instead of epsilon sub 1, I write n sub 1 times E, right? Instead of K times T, I write E. These two E's cancel each other, and n sub 1 is equal to 1. In other words, we got E raised to minus first, right? Okay, similarly, we will get that exponent raised to minus epsilon sub 2 times over k times t is equal to e raised to minus the second, etc., etc. We got e raised to minus third, e raised to minus the fourth. Okay, and now we are ready to calculate the level populations for each of the energetic levels for the ground state n sub 0 over n, it's equal to a raised to minus epsilon sub 0 k2 over the sum of all these Boltzmann factors. Okay, for this particular ground state level, the level population is equal to 1 over 1 plus a raised to minus 1 plus e raised to minus 2 plus e raised to minus 3, yeah, and of course e raised to minus 4. So we need a calculator, and it's equal to 0.6364. You see, now we are getting another picture. Now the um, first level population is equal to n sub 1 over n, and is equal e raised to the minus first over 1 plus e raised to minus 1 plus e raised to minus 2, blah, 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 the same, okay? And your calculator should show you that the answer is equal to 0.2341. You see, these numbers are quite impressive, I guess. Now, for the next energetic level, its level population is equal to n sub 2 over n, and is equal e raised to the minus second degree over this denominator plus blah 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 blah. Okay, and it's equal to 0.060, I'm sorry, 8613. The population of the next level is equal to n sub 3 over n, and is equal e raised to minus third over 1 plus e raised to minus 1, blah 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 blah, and that will give you 0.03168. And the last, but not the least, here, as they say, n.4 over n is equal to exponent raised to the minus fourth over the sum, and that's equal to 0.01166. 1166, right? And also we need an sub 5 over n, because we got, if you remember, n is equal to 0, 1, 2, 3, 4, and 5. Oh yeah, you may say, and why didn't we calculate the fifth level in the case of low temperatures? Yeah, that's my fault, frankly speaking. I got this, I got some issue to do immediately. Sorry, but that's why I forgot to do that. But in practical terms, that played no role at all, because it would have been a much less than the last neglected term, and it would have played no role at all, but not in this case. So n sub 5 over n is equal to, if you continue the calculation, so it's e raised to minus 5, right, over this sum minus 1 plus e minus 2, blah blah blah. So let me have a look. I need to calculate, I'm sorry. So e raised to minus 5, and we divide it by 1 plus e minus 1 plus e minus 2 plus mm, minus 3 plus minus 4 and plus a raised to minus 3. Okay, and we got, yeah, we got it. It's 4.27 times 10 raised to minus the third. Okay, yeah. And now, having calculated the energy level populations for all the energetic levels, we can start calculating the average temperature for the second case. At average temperatures, it's equal to the sum of multiplication of energy of each level by its level population. Okay, let's do that. So it's 0 times 23, 41 m times A plus hold on a second, please. And it's not this one, is it this one? 63, 64 plus the next one, 23, 41 E. Yeah, we remember that E is equal n times E, where n is the number of the level for the ground state is equal to 0. For the first level is equal to 1, but okay, I'll write it here, 1. Then plus for the second, it's 2 and is equal to 2 double E times 0.08613 plus 3 times E times 0.03168 plus 4 times E times 0.01166 and plus 5 times E times 4.27 times 10 raised to minus 3. And finally, we got 0.567 times E. And this is the answer. As you see, at average temperatures, the average temperature supply is equal to 0.567, and it is not much more than that at low temperatures. It's logical, but the principle of the calculation is the same absolutely. And we have been through with calculations at average temperatures, and we've got this result. And now we are going to proceed to the segment of high temperatures, and we can do it automatically, I guess, because the calculation will be absolutely identical. Absolutely identical. Let's get started then. Okay, on the second page, I need to see the numbers. Yeah, here they are. Okay, for the high temperatures, it's part 3 of our calculations. High temperatures. When K times T is equal to 10 times A. Okay, so the exponent raised to minus epsilon sub 0 over KT is equal to exponent raised to 0 and is equal to 1 provisional. Okay, then for the next, for the first level, A raised to minus epsilon sub 1 over kt is equal to e raised to minus um, um, instead of epsilon e, we write n sub 1 times e, and instead of kt, we write 10 times e. But n sub 1 is equal to 1 because now we are talking about the first level, which is next from the ground state, and we got e raised to minus a 10, right? And similarly, we will get the following uh, values of Boltzmann factors for each of the levels, and e raised to minus 0.5. So I guess it's clear. I hope that it is clear. And now we are ready to start calculating the Angelo populations for each of the levels. So n sub 0 over n is equal to uh, epsilon, I'm sorry, e raised to minus epsilon sub 0 over kt. And we can write sigma e raised to minus epsilon over kt. And it means 1 over, yes, this equals is equal to 1 plus e raised to minus 0.1 plus e raised to minus 0.2. Okay, this time I write it fully. Okay, and if you got a calculator, you will get that it's equal to, it's 1 over 4.741. This will need is for the rest of the calculations, right? And it's equal to 0.211. Now for the next level population, it's equal to e raised to minus epsilon sub 1 over kt. And this, the denominator is equal to e raised to minus 0.1 over this one. And it's equal to 1909. Likewise, n sub 2 over n is equal to epsilon raised to minus, I'm sorry, e raised to minus epsilon sub 2 over kt over the sigma of, I'm sorry, exponents raised to minus epsilon I over kt, and it's equal e raised to the minus 0.2 over 4.741. Again, this number is equal to this sum. Just to minimize the save on the computer, I'm not writing this denominator in the full. I'm writing its final. So, and it's equal to 0.1727. And without further writing in detail, I will write only the finals, the answers. So, and n over n sub 3 over n is equal to 0.1563. N sub 4 over n is equal to 0.4414. And n sub 5 over n is equal to 0.1279. So we have just calculated the Angelo populations for each of the discrete energetic levels, and now we are ready to calculate the average temperature, the average energy. This is the general formula, and now let's do that. The energy for the ground state is equal to 0, but let us write it in detail, plus for the next level, its number is 1. Instead of writing n sub 2, I'm writing 1 energy, right? And the population of this level is equal to 1909, right? For the next level is n sub 2. So NE for this level is equal to 2 times E. Okay, and 0.1727 plus 3 E times 0.1563 plus 4 times E multiplied by 0.414 plus 5 times E multiplied by 0.1279, and your calculator should show you this number 2.2103 times E. Here it is. This is the answer for the answer what is the average energy of the system is equal to at high temperatures. The calculations are absolutely identical. I'm sorry that at times I made some mistakes. It's because I was distracted by my cats. Sorry, sorry about it. Okay, but the answers are correct. Believe me, the answers are correct, and the whole calculation algorithm is correct too. Just want you to I want to emphasize the importance of the logical steps of the calculation. The first one is calculating the energy level populations, and if nothing is said about the statistical weight, so we get in a word with that its weight is equal to 1, and in practical terms we understand that they play no role. Also, after that we start calculating the after Boltzmann factor calculations, we start calculating energy level populations. And after that, we can start calculating the average energy of the system. Thank you. Now let's proceed to the next problem. It's interesting. Here it is. The molecule can occupy the ground state and 3 other energetic levels of the same energy E. Calculate the average energy of the molecule at in two cases, at very low temperatures and very high temperatures. As you see, the difference between this problem and the previous one is that they don't particularize the value of the temperatures. In other words, we will have to apply some mathematical techniques taken from advanced mathematics to get the right answers. Okay, let's start from the first part, which is very, very low temperatures. Okay, so traditionally we are going to start from calculating Boltzmann factors, and for the ground state is equal to minus, so epsilon sub 0 over kt, right? But we understand that it's traditionally in statistical mechanics we presume that the energy of the ground state is equal to 0, right? And for that reason, its energy is equal to, I'm sorry, its Boltzmann constant, oh my God, its Boltzmann factor is equal to 1. Now, for the next level, the Boltzmann factor is equal to minus epsilon times sub 1 over k2. Okay, and it's equal to this, because from the problem we see that for all the other levels, the energy is equal to E. It's not E sub 1, it's equal E, just E. E over K times 2. Okay, right, and this is the same for the other levels, but let me draw it. So this is the ground state, yes, and we've got three other levels here in 1 and 2 and 3, but the energy of these three levels is the same. E, E, and E. This here it's 0. We've got three levels of the same energy, and that means one thing clearly, that we've got finally statistical weight, yes, G, which is equal to 3. This is very important to bear in mind. Now, now, in other words, we can write that the statistical weight for non-ground states is equal to 3 non-ground states. Now, let's write down or let's calculate the energy populations, right? Okay, n sub 0 over n is equal to a Boltzmann factor to the sum, but this time we should take into consideration this statistical weight G I times exponent raised to minus epsilon I over kt. And for this particular level, which is ground state, we write 1. Okay, it's okay, I have already written it down. Okay, now I know this is equal to 1, and here I write the sum 1 plus G is equal to 3, because the number of the levels of the same energy is equal to 3. 3 E, which is exponent raised to minus energy divided by K2. Okay, yeah. Now, N sub 1 over N is equal to G E minus raised to minus E over K2 to the sum, right? G is equal to 3. This one is E exponent raised to minus E divided by K2, and the denominator is the same. Okay, okay. Now, what we do is calculating the average energy, which is equal to the sum of the production of the energy of each of the level by the energy level population. Okay, for the ground state. And for the other three levels, right? And that's equal to 0 for the version. Finally, we got the following. It's 3 E times exponent raised to minus energy E divided by kt over 1 plus 3 times e raised to minus e over kt. Yeah. In order to make our further calculations easier, let's divide the numerator and the denominator by this exponent, and we will finally get 3e over uh, exponent raised to e over r kt plus 3. Yeah. And now, again, we have no idea about the exact value of low temperatures, but in this case, we can use limits, the theory of limits. The limit of this fraction, I'm sorry, plus over kt plus 3, when t uh, gets closer to 0, because at low temperatures, that means this one, we've got 3 times e over. Now, t is equal to 0, right? And that means that the denominator of denominator uh, leads to or approaches to a very, very small, infinitely small number, but it is in the denominator, which means that on the whole of this degree approaches to plus infinity, and exponent raised to plus infinity gives plus infinity. And plus infinity plus 3 is equal to infinity, but in this case, infinity is in the denominator. For that reason, this limit is equal to 0. For that reason, we can say that at low temperatures, the energy, the average energy, is equal to 0. Now, case B, very high temperatures, very high temperatures. In this case, we will get the same, but the limit is slightly different. In this case, 2 goes further to plus infinity, right? In this case, k times 2 goes to infinity 2, but it is in the denominator. For that reason, this degree gets closer to 0, and exponent raised to 0 is getting closer to 1, right? And we got the following: 3 times e over 1 plus 3. That means 3 times e over 4, or 0.75 times e. This is the answer for the case when we got very, very high temperatures. As you can see, without mathematics, we cannot go further. I hope that it is clear for you. Again, this is the matter, or the foundation of the solution is in the theory of limits. It's very easy to understand. Let me write down here separately. So E over K times T. E and K are two constants. For that reason, the value of T plays the important vital role. If T is getting closer to 0, we will get that. Let's see that. It's E over K. Let's take a very small one, for example, 0.0001. In this case, we will get that it's equal to 1.0000 E over K. And if we get even less than this number, we will get even more than this one, which means that it's uh, goes to plus infinity. For that reason, and exponent raised to infinity also goes to plus infinity, but it's all is in the denominator. And when we divide some constant to infinity, that gives us 0 finally in the limit. But in this case, again, it's e over k times t. When t goes to infinity, let's take a very big number, for example, e over k, and let's take a million, okay, 10 raised to the sixth, but it is in the denominator. This number gets very high, but we will get to this very high number, right? And finally, in the limit, it goes to infinity, positive infinity. But this infinity is in the denominator, which means that when we divide some constant to the infinity, we got very small number. In limit, it is equal to 0, right? But this is the degree. So exponent raised to the degree of 0 is equal to 1. For that reason, I wrote 1 here. And 1 plus 3 is equal to 4, etc. I hope that it was clear for you. Thank you.